All right, so let's look at one more tactic to help us with multi-step synthesis. And this is something that we call retrosynthesis, where we basically look at our target and work backwards. When I was a kid, I loved to do mazes. And for some reason, maybe it's just because I'm weird, I always started at the end and worked back to the beginning because that was a lot easier for me for some reason. And that's kind of what retrosynthesis is we look at the end goal and we try to imagine what the last reaction would have been. And then we go back one more step and go back one more step. And then by the time we go back far enough, we're back at our starting material. And that's kind of like an ideal world. What we really, at least what works for me, is I might go backwards a couple steps and then I'll go start at the beginning and go forward and meet in the middle. Whatever tactic works for you, is what I'm going to tell you to do. And so sometimes retrosynthesis doesn't work for certain people for certain synthesis, and that's fine. This is not a requirement. This is just a tactic that you could use if it is helpful to you. And when you look at your target, you need to ask yourself three questions. Number one, did the number of carbons change? And when I say change, did we add carbons or did we take away carbons? Or another answer could be nothing happened, and that's fine. Okay, so again, think about it. If you added carbons, we only know one way to do that. If you took away carbons, we only know one way to do that. So make it simple on yourself right now and know those methods. Number two, ask yourself, did the functional groups change or move? And or move, I should say. Okay. So again, how do we move groups around through that elimination addition process? How do groups change? Well, maybe through substitution or through like an elimination and then add a different group on. And then number three, when you look at the product, you need to look at stereochemistry and or regiochemistry. Now, you might not have one or both of those. You might have to deal with both of them, but that's always a question you need to ask yourself. All right, so I'm going to do a couple examples in this video. I'll do a couple more in another one. So let's start here with this alkyne. And we're going to make this alkene. This is how a typical exam problem is going to look for multi-step synthesis. I'm going to give you what you can start with. I'm going to give you your target, and then I'm going to want you to draw all the reactions in between that will get you there. Not just the reagents. You don't just list the reagents you think you're going to need. You need to show the result of every step as well. So let's ask ourselves our three questions. Number one, was there a change in carbons? Well, in order to do that, let's do some numbering here. Let's go like this. 1, 2, 3, 4, 5, and 6. And then we'll do the same thing here. 1, 2, 3, 4, 5, 6. And it looks like I added carbon 7 and 8. So I added 2 carbons. Was there a functional group change? Well, yeah, I started with an alkyne and ended up with an alkene. And then number 3, do I have to deal with any stereochemistry or regiochemistry? I want you to look really closely at our target. Look at carbons 5 and 6. Is that a stereo-specific double bond? Is there any stereochemistry to that? Yeah, that's a cis alkene. So my reactions need to address all three of these things. I need to add carbons. I need to convert an alkyne to an alkene, but not only that, I need to make it a cis alkene. Okay. Now, as a little hint, you generally want to add the carbons first because once you go away from an alkyne, you can no longer add carbons. Okay. So keep that in the back of your mind. Now, what I'm going to do is I'm going to work backwards a little bit. I'm going to imagine the final step here in making that cis alkene. Now, what's the only way that we know how to make a cis alkene? We need to start with an alkyne, and I'm going to number these again. 1, 2, 3, 4, 5, 6, 7, 8. And what are the reagents that you need to make a cis alkene? Okay, I want you to kind of yell them out at your computer screen. You say, if the answer to that is I don't know, like if you don't, without having, you shouldn't have to look back in your notes. Then you need to go back and look at the reactions from this unit. We're going to use H2 and then there's catalyst. Okay. Now, if we look at where we're at now, I'm starting with a 6-carbon terminal alkyne and I'm adding 2 carbons to it. What is the only way that we know how to add carbons? We're going to deprotonate this terminal alkyne. To make an acetylide ion. So again, I'm going to number these 1, 2, 3, 4, 5, and 6. And then what do I have to add to this to get my 2 carbons? Again, you should be able to notate that without having to look back at your notes. And we add a 2-carbon alkyl halide. It'll do an SN2 on it. And that will finish up our synthesis. So notice I kind of did a combination of like I went backwards one step and then I started at the beginning and went forward and met in the middle. And that's fine. As I said, I am not going to require you to do retrosynthesis. It's just a tactic that has helped and can help in a lot of different problems. All right, let's look at another one. So we're going to start with this alcohol and we're going to make this aldehyde. Now let's ask ourselves our 3 questions. Number 1, did the number of carbons change? Well, if the cyclohexane looks the same, but if I count the carbons outside, I got carbon 1 and 2 there. And how many carbons are outside the ring now? Just 1. So that tells me I removed a carbon. I'm going to ask you, what is the only way that you know how to remove carbons? Oxidative cleavage. The second question we ask ourselves, was there a change in functional group? Okay, so notice on carbon number 1, there's still an oxygen, so I didn't move anything, but I did convert an alcohol to an aldehyde. And then number 3, do I need to worry about stereochemistry or regiochemistry? Well, my product isn't chiral, so no stereochem. And it looks like everything happened on carbon number 1, so there's no regiochemistry. Okay, so let's work backwards again. Again, what is the only way that I know how to remove carbons? Well, I'm going to do an oxidative cleavage of an alkene. Now, why an alkene? Because I want to make an aldehyde. And the only way I can make an aldehyde, not an carboxylic acid, is to start with an alkene. And notice I'm still got my 2-carbon skeleton here. But once I do the oxidative cleavage, Then I get rid of carbon 2. Where's carbon 2? Well, it's floating around literally as carbon dioxide. There's carbon 2. All right, now if I look and see what my remaining tactic has to be to go from an alcohol to an alkene, I want you to note a couple things. First of all, OH, is that a good leaving group? No, it's not. Okay. Secondly, what kind of elimination has to happen in order to get that double bond between number one and two? I have to do a Hoffman elimination. Okay. Let's deal with OH being a poor leaving group because we're not going to eliminate it in a Hoffman style. So one common tactic is make it a good leaving group with tosyl chloride in pyridine. That makes it an OTS group. Again, here's carbon 1 and 2. Now it's a good leaving group, so now I can do my Hoffman elimination. And what kind of base do I need for that? I need a strong, bulky base. So let's go with like DBU. All right, again, notice I didn't go completely backwards. So it's not a requirement that you go from the end all the way back to the beginning. Like I said, I usually will go back a couple of steps, one or two steps, and then go start at the beginning and go forward. And most of the time, I end up meeting in the middle. So in the last video, I'm going to do a few more examples of multi-step synthesis.